All right, I guess this is probably it for today. I normally see about 20 attendees, but I guess oh, is it the midterm week this week? 이번이 혹시 그 중간 그 고사 기간인가요? 아, 그래서 그렇구나. 네. Okay, yeah. So yeah, the course schedule for this class is a bit different from the others, where other classes we normally have like a midterm weekend, the final week off. But because since we have like 3 projects instead of homeworks and projects, I decided that there should be just 3. Yeah, we should have like a slightly different schedule. So that's good. All right, we'll just go with 17 people today, which would be a bit unfortunate because today actually I invited one of the students who actually performed really phenomenally well for the regarding the project number 1. So I asked the student, so the name of the student is Junwoo 박준우님. 그러니까 박준우님께서 그 0.4 AUPRC가 굉장히 높으셔가지고 이제 그걸 좀 얘기를 들었는데 이제 굉장히 좀 이 피처 엔지니어링 여러 가지 프로세싱을 열심히 하셔가지고 이제 어떻게 하는 그 방법들을 좀 공유를 해주실 수 있나 다른 학생들하고 한 10분, 15분 정도만 발표를 부탁드렸거든요. 그래서 그거를 좀 들으려고 했는데 많이들 오셨으면 좋았을 텐데 또 아쉽게도 오늘 또 중간고사 기간이어가지고 그렇지 못하네요. So yeah, I just briefly said that I asked Junwoo Park, who actually scored a really high AUPRC for the both logistic regression and RNN in our project number 1. So I invited him to give us like maybe 10 or 15 minute talk. 10 or 15 minute casual talk on how he did all the pre-processing and the feature engineering, the model training and all that. So if you are ready, 준호님 혹시 준비가 되셨으면 지금 시작해 주실 수 있을까요?
네. 혹시 들리시나요?
네, 잘 들립니다. And additionally, I'm sorry, but since Junwoo Mr. Junwoo Park asked to present in Korean, so this would be a Korean-only session for 10 or 15 minutes, but the slides would actually be self-explanatory, hopefully, so that would be okay. So let's welcome Junwoo Park, and 준우님 그럼 스크린 쉐어 부탁드리겠습니다.
네. 보이시나요?
네, 잘 보입니다.
네, 그럼 진행하겠습니다.
네.
네, 이번에 이제 첫 번째 과제로 이제 저희가 이제 ICU 모탈리티 프리딕션을 진행을 했었는데요. 거기서 뭐 점수가 꽤 잘 나왔고, 그래서 그거에 대해서 공유를 부탁받아서 진행하게 되었습니다. 저는 주재구 교수님 연구실의 박준우이고요. 일단은 좀 간단하게 좀 핵심적인 것만 준비를 했는데요. 일단은 지금 보시는 이 그래프는 제가 이제 실험했던 것들을 이제 Y축이 이제 스코어이고, 이제 뭐 AUPIC나 이제 AUROC 그리고 ACC 이렇게 3가지가 이제 그래프로 나와 있는데, 이제 밑에 X축은 이제 제가 모델에 사용했던 이제 피처의 디멘전 수이거든요. 그래서 피처 디멘전 수가 변함에 따라서 성능 증가하는 그래프 양상을 보이는데요. 이때 이제 2가지 성능 향상이 크게 일어난 부분이 있는데, 하나는 이제 차트 이벤트를 전혀 쓰지 않았을 때와 차트 이벤트에서 10개 아이템을 골라서 썼을 때, 이때가 이제 성능 향상이 크게 있었고,
준우님 지금 그 론리 스크린 에어플레이
네.
리시버 네네.
크게 있었고, 그 다음에 이제 아이템 수를 이제 30에서 이제 300개로 굉장히 크게 올렸을 때 여기 성능 향상이 이제 2번 크게 있었고요. 지금 보면은 이제 노 차트 이벤트라고 이제 제가 명시를 한 것은 이제 이거는 이제 차트 이벤트 그러니까 시퀀스 데이터가 없이 그냥 단순히 이제 페이션트가 가질 수 있는 정보들이나 아니면 ICU 스테이에서 가질 수 있는 어트리뷰트들만 사용했을 때입니다. 네, 그랬을 때는 스코어가 AU 이제 PIC가 이제 성능이 저희가 안 나오다 보니까 AU PIC 기준으로만 보면은 저도 차트 이벤트를 쓰지 않았을 때는 0.1 조금 넘은 수준에서 나왔었거든요. 근데 이제 차트 이벤트 아이템에서 이제 센싱된 아이템들을 이제 잘 피처 엔지니어링을 통해서 이제 벡터로 만들고 이제 그거를 로지스틱 리그레션 썼을 때 성능이 크게 올랐었고요. 결국에는 이제 여기서 성능 형성이 크게 일어나는 거는 결국에 이제 차트 이벤트에서 얼마나 많은 이제 아이템들을 잘 골라서 피처로 추가를 했느냐가 이제 성능을 올릴 수 있는 네, 그 요인이 되었던 것 같습니다. 네, 이게 좀 핵심적인 거고 이제 그 아이템을 이제 차트 이벤트에 이제 유니크한 아이템 수가 이제 한 2,600개 정도로 기억을 하거든요. 그 환자들 이제 저희가 이제 선택한 이제 ICU 그 기준으로 봤을 때 한 2,600개 유니크한 아이템들이 있는데 300개 이상부터는 성능 향상이 미비하고요. 그 이유를 생각해 보면은 이제 이 아이템들이 모든 환자들한테 다 이렇게 센싱이 되진 않았거든요. 그래서 어떤 아이템 아이디는 뭐 특정 환자 두세 명한테만 존재하는 아이템들도 있고, 그리고 뭐 하트레이트 같은 경우에는 모든 환자들이 갖고 있기도 하고요. 그래서 아이템을 아무리 많이 늘려봤자 300개 이상부터는 이제 성능 향상은 딱히 보이지 않았었고요. 그다음에 뭐 피처 셀렉션 같은 거를 진행을 해서, 왜냐면 제가 너무 많은 아이템을 넣기 때문에 여기서 이제 성능과는 이제 인디펜던트한 피처들도 있을 수가 있거든요. 이제 그것들을 이제 가려내주기 위해서 이제 피처 셀렉션 메서드를 몇 개 써봤는데, 뭐 그때도 피처 디멘전이 이렇게 줄어드는 거 외에는 뭐 특별한 성능 향상은 없었습니다. 이게 제가 이 과제를 진행하면서 성능을 올릴 수 있었던 그런 핵심적인 부분들을 보여주는 거고요. 그래서 저는 그러니까 왜 이렇게 진행을 했느냐에 대해서 또 설명을 드리면, 일단은 저는 헬스케어 자체에 대해서는 그렇게 도메인 알리가 없거든요. 사실 뭐 저도 뭐 대부분이 그렇겠지만, 저도 생각을 해보면은 하트레이트가 이제 낮아질 때 사람이 죽을지 아니면 너무 높아졌을 때 죽을지 이런 것도 좀 감이 없기도 하고, 그 외에 이제 뭐 다이그노시스 같은 거 보면은 뭐 병명 같은 것도 다 인터넷 쳐봐야 알 수 있고, 사실 그래서 뭔가 제 도메인 날리지 이용해서 피처 셀렉션을 하거나 뭐 그런 것들이 좀 불가했었고요. 그래서 할 수 있는 거는 최대한 그 스태티스를 이용해서 어떤 피처를 사용할지, 뭐 예를 들어서 코릴레이션이 높은 피처들을 골라본다든지. 근데 뭐 사실 코릴레이션 같은 거를 봐도 그 데스 레이블과 그렇게 이제 코릴레이션이 큰 피처들은 없더라고요. 그래서 생각을 한 게, 일단은 내가 사용할 수 있는 그 피처를 가능한 많이 사용을 하자였고요. 그때 이제 피처를 고르는 기준은 이제 페이션트나 이제 ICU 스테이 기준으로 가장 많이 이제 레코디드 된 순서대로, 그러니까 탑 K개를 뽑아서 이제 뭐 이 K를 늘려가면서 이제 성능 테스트를 했었고요. 그래서 이렇게 그 이제 피처를 늘려가다 보면은 오버피팅이라 의심될 만한 상황이 올 수가 있거든요. 그때는 이제 레귤라이저나 이제 피처 셀렉션 메서드를 이용해서 피처 디멘전을 줄여주거나, 아니면은 이제 그거를 좀 감소시키는 형태로 오버피팅을 이제 좀 줄일 수 있는 방법들을 사용을 했고요. 예를 들어서 로이스트 리액션 같은 경우에는 이 상수 C가 이제 하이퍼 파라미터로서 이제 레귤라이저 역할을 하니까요. 그리고 피처 셀렉션 같은 경우에는 카이스케어 피처 셀렉션 메서드 썼는데, 뭐 이게 특별한 이유는 있는 건 아니고, 제 경험적으로 봤을 때 이게 NLP에서 배그 오브 월즈를 썼을 때 좀 성능이 괜찮은 걸로 기억을 하고 있는데, 그 차트 이벤트 중에서 이제 카테고리컬 아이템들이 이제 배그 오브 썸이 될 수가 있거든요. 배그 오브 월즈가 될 수 있는데, 이때 이 부분에 대해서 뭐 해볼 수 있겠다 싶어서 쓴 거였는데, 뭐 이거 두 개가 완전히 같지는 않지만 둘 다 이제 오버피팅을 좀 막아줄 수 있는 효과를 가져올 수 있고요. 그리고 이제 프리 프로세싱에 대해서 간략히 언급을 드리면요, 사실 이걸 프리 프로세싱을 모든 걸 다 말하면은 끝도 없거든요. 이렇게 뭐 스케일러부터 시작을 해가지고 미싱 밸류 어떻게 처리할 건지, 아니면은 그 프리퀀시가 너무 낮은 애들은 또 어떻게 처리할 건지, 뭐 이런 것들을 다 따지다 보면은 사실 너무 길어질 것 같아서, 좀 가장 좀 굵직한 것만 얘기 들면은, 일단은 저희가 갖고 있는 데이터셋에서 이제 크게 두 가지 타입으로 이제 밸류들을 구분할 수가 있는데, 하나는 이제 뉴머릭 밸류들, 그리고 하나는 이제 카트리콜 밸류들인데요. 뭐 대표적인 게 얘 같은 경우에는 이제 뭐 하트레이트가 있을 수가 있고, 얘 같은 경우 다이고노시스 이제 시스가 될 수가 있는데, 이거 두 개를 각각 어떻게 처리했는지에 대해서 말씀을 드리면은, 일단 뉴머릭 밸류 같은 경우에는 이게 저희가 이제 차트 이벤트 아이템 보면은 이게 타임 스탬프가 이제 규칙적으로 찍혀 있는 게 아니라 이제 이레귤러하게 찍혀 있거든요. 뭐 15분 간격일 때도 있고 어쨌든 1시간 간격일 때도 있고요. 그래서 이거를 일단은 미싱 밸류 채우는 것 자체가 약간은 좀 너무 뭐 평균을 채운다든가 아니면 뭐 다른 방법들 이용해서 예측해서 채울 수가 있을 텐데 그게 좀 번거롭기도 하고 그거 자체가 이제 맞을지 확신도 없기도 해서 일단은 이레귤러한 밸류 시퀀스가 있으면은 이제 ICU 기준으로 해서 이제 그룹핑을 한 다음에 거기서 이제 민과 맥스 그다음에 최소값 이렇게 세 가지를 뽑아서 피처로 만들었거든요. 그래서 한 개의 아이템이 이제 3차원의 피처 디멘전을 갖게 되고요. 그다음에 이제 카테고리컬 밸류 같은 경우에는 일단은 카테고리컬 밸류를 처리하기 위해서 이제 이 카테고리 밸류가 스트링 타입이니까 이거를 저희가 이제 수치로 바꿀 필요가 있거든요. 그 바꾸기 위해서 뭐 가장 흔히 쓰는 방법이 이제 원하는 코딩이니까 뭐 카테고리컬 밸류가 B가 있으면은 이거를 이제 뭐 이런 식으로 이제 만들어 볼 수가 있을 거고 이게 만약에 한 환자한테 일어난 일이라고 한다면은 이 환자 한 명에 대해서 이제 한 ICU 스테이 하나라에서 일어난 그러니까 측정이 된 이제 그 아이템들이라면은 이거를 이제 이 ICU 스테이 하나에 대해서 이제 벡터로 만들어야 되니까 이제 얘를 썸을 할 수가 있거든요. 그러면은 이제 얘가 뭐 이런 식으로 이제 백오버즈가 될 수가 있겠죠. 그래서 이거를 이제 벡터로 써서 처리를 했고요. 근데 이게 사실 이건 약간 엔지니어링적이긴 한데 제가 이제 피처를 거의 이제 1000개 그러니까 아이템 수를 차트 이벤트에서 1000개까지 테스트를 해왔거든요. 근데 그거를 하는데 일단은 이게 한 ICU 스테이에 그 다음에 이제 한 ICU 스테이에 또 아이템들이 여러 개가 있고 그 다음에 이제 밸류가 있는 구조로 테이블이 설계가 돼 있는데 이럴 때 이제 이거를 결국에 이제 그룹핑을 해야 되잖아요. ICU 때 하나로 그룹핑을 해야 되고 거기서 또 아이템들을 각각 그룹핑을 해서 이제 뭐 배그 오브 썸을 하든 배그 오브 월드를 하든지 이제 뭐 민 맥스를 구하든지 이렇게 해야 되는데 이때 이거를 파이썬 포룹 같은 걸 돌려서 하면은 시간적으로 아예 답이 없어서 일단은 이런 과정들을 진행할 때 모든 걸 전부 다 판타스에서 가지고 있는 펑션들로 진행을 해야만 가능하고요. 안 그러면 데이터 수도 워낙 많기 때문에 시간적으로 테스트하기가 좀 힘들거든요. 그래서 그때 뭐 저는 주로 이제 판다스에서 제공하는 머지 펑션이나 아니면 그룹 바이, 이 어플라이 같은 거 3개를 이용해서 이제 포룹 없이 진행을 했고요. 결국에는 이게 또 결국에 과제 마감도 있고 시간이 좀 중요하기 때문에 이런 판다스 펑션들을 적극적으로 이용을 하는 게 더 많은 실험을 할 수 있는 뭐 그런 요인이 되었던 것 같습니다. 뭐 여기까지가 제가 오늘 그 과제 1에 대해서 이제 말씀드릴 내용이고요. 뭐 혹시 질문이 있으실까요?
지금 채팅창 보시면은 그 소로가 질문을 했는데 연속으로 2개 질문해 주셨네요. 혹시 좀 답을 해주실 수 있을까요?
네, 잠시만요. 이게 제가 공유한 상태에서 채팅이 잘 안 보여가지고. 보이네요.
제가 불러드릴게요. 그 첫 번째
네.
질문이 How do you get feature dimension 2? 그러니까 이제 2219차원 이 피처 디멘션이 나왔는데 사용한 아이템 아이디는 300개밖에. 이거 첫 번째 페이지 보여주실래요 혹시?
네네네. 네.
여기는 네, 여기서 이제 차트 이벤트 아이템은 이제 300개를 썼는데 어떻게 피처 디멘션 2219개가 나왔냐 이런 질문이거든요.
네. 영어로 설명드려야 될 것 같은데 일단은 일단은 뭐 그 한국어로 설명해주면은 소로님이 이해를 하실까요?
뭐 영어로 한번 해주실 수 있으면 아니면 뭐 한글로 지금 제가 대신 답해드려도 되고요. 편하신
네.
대로 하세요. 네네.
네, 죄송합니다. 일단은 아이템이 이제 뉴머릭 밸류가 이제 뉴머릭 밸류를 가지는 아이템 같은 경우에는 여기서 보듯이 이제 한 개의 이제 아이템이 이제 밸류 이제 이게 세 개의 피처 디멘전이 될 수가 있는 거거든요.
그쵸.
네, 왜냐면은 제가 민과 맥스, 그러니까 민과 맥스와 이제 민값을 뽑았으니까 그래서 이제 한 개의 아이템이 이제 세 개의 피처 디멘전으로 늘어나는 경우고요.
네.
그다음에 이 카테고리컬 밸류 같은 경우에는 그 이제 갖고 있는 카테고리의 수가 굉장히 많을 수가 있거든요. 그래서 아이템이 한 개더라도 카테고리컬 밸류면은 갖고 있는 그 아이템 수만큼 갖고 있는 카테고리 수만큼 늘어나요. 그래서 아이템이 한 개의 경우에 뭐 카테고리 밸류가 뭐 종류가 20개가 있다 하면은 그 피처 디멘전이 한 개에서 20개가 되는 거고요.
그러니까 뭐 에스니시티나 이런 거 말씀하시는 거죠?
네, 맞습니다.
네네네. 네. 그렇게 해서
그래서
이제 한 7배 정도 뿌른 거다 라시는 거죠?
네네네.
네네. 제가 그 설명을 좀 해드릴게요. 그럼, so Sora, as for your first question, as you can see here in this slide, page number 4, a single numeric value is represented by 3-dimensional vectors, each dimension representing mean and the maximum and the minimum value for that specific numeric feature. You know, like for heart rate, what is the mean value of the heart rate and what is the maximum or the minimum of the heart rate? So that would be 1-dimensional numeric feature being increased to 3-dimensional vector space, about 3-dimensional vector. And as for the categorical values, some category values actually have a lot of classes or a lot of categories. For example, like ethnicity, I think the mimicry ethnicity has about 15 categories or 20 categories or something like that. So yeah, so some categorical features contain only few, like maybe, for example, like gender would be only 2 categories, but as I said, ethnicities are some like 15 or 20 categories. So that also is a factor that, you know, that decided the total number of feature dimensions to 2,200 when the actual number of features are only 300. So does that answer your question? All right.
두 번째 질문 같은 경우에는
네.
이제 그 차트 이벤트 테이블이 ICU 스테이와 이제 아이템 아이디 이제 두 개가 이제 로우로 이제 풀어져 있는 형태이거든요. 그래서 그거를 이제 그룹 바이 할 때 멀티플 인덱스를 쓸 수가 있어요. 네, 그래서 첫 번째 인덱스로 ICU 스테이 아이디를 주고 그 다음에 이제 아이템 아이디 인덱스를 주면은 이제 그 다음에 그룹 바이 펑션에 어그리게이션 펑션에 이제 민이나 맥스 뭐 민값을 쓰면은 이제 그게 두 가지 이제 멀티플 그룹 바이가 돼서 이제
네네.
값을 이제 얻을 수가 있고요.
그러니까 그룹 바이에서 키를 튜플로 쓴다는 거죠?
네, 맞습니다.
네네. 그러니까 have you group by? So Sora, as for your second question, have you group by or just group by text? So what Junwoo just answered to that question is, so he used a tuple, a 2-dimensional tuple, as the key for grouping to perform the group by action. So the tuple being IC stay ID and the item ID. So he actually used those two columns. Yeah, I would say two. So 2 columns to form a single tuple, and then use that tuple as a key to do the group by action. Is that clear? Alright, cool. 저도 사실 궁금한 게 있는데 요 마지막에 펜더스 펑션들 이제 적극적으로 사용하셨다고 하셨는데 그 펜더스 이제 클래스에 많이 올라온 질문이 펜더스로 그 데이터 프레임을 로드하려면은 차트 이벤트가 너무 커서 안 된다 이러는데 그 어떻게 하셨나요?
일단은 그거는 제 생각에는 이제 리드 CSV에서 청크 사이즈 옵션이 있잖아요. 아규먼트 있는데 그게 청크만큼 이제 이터레이터를 만들어가지고 루프에서 부르는 건데
네.
결국에 저희가 3억 개 롤 다 쓸 필요가 없고 저희가 이제 관심이 있는 ICU 스테이트 아이디 리스트가 있잖아요.
그렇죠. 네.
이제 전체 한 5만 개가 6만 개 정도 ICU 중에서 이제 15,000개인데
그렇죠.
그래서 차트 이벤트 3억 개가 다 필요가 없어서 한 100만 개씩 부른 다음에 걔랑 이제 그 ICU 스테이 아이디 리스트랑 저희 갖고 있는 거랑 이제 그 필터링을 해가지고 그 100만 개 중에 일부를 추린 다음에 그 다음 루프에서 나온 것과 이제 계속 그 머징을 하면서 이제 키워 나가는 거죠. 그렇게 하면 100만 개씩 처리를 하는 거고 그 다음에 이제 전체적으로 3억 개가 이제 2,600만 개로 줄거든요.
그쵸?
이제 그때부터는 쉽게 처리가 가능한 상태가 되고요.
아, 그럼 600만 개 정도는 이제 메모리 올리는데 문제가 없는 거고요.
네, 봤는데 가끔 그 사람들이 3억 개 전부 다 메모리 올려가지고 하면은 한 250기가 정도 되더라고요.
네.
근데 2,600만 개 하면은 한 2, 30기가 정도 되는데 뭐 충분히 처리하는데 문제는 없습니다. 요즘 컴퓨터 좋아서.
네, 알겠습니다. 네, 감사합니다. 소로가 잠깐. So, Soro, your final comment is the same. That is true. Yeah. So I believe the same ICU stay IDs is. What? I believe this. Is that true? You mean the same like two different patients can share the same ICU stay ID? That is not supposed to happen. So if there is a case like that, then that is definitely an error or like typo or something. So the human annotators who store the data into the ICU, EHR software, they probably made a mistake or something. So you can assume that ICU stay IDs are unique identifiers for each individual ICU stay. So so even for like the same patient, the same like a single individual patient can have multiple ICU stay IDs, and those set of ICU stay IDs should never overlap with ICU stay IDs from another patient. So what Junwoo did in the pre-processing step actually is logically correct. And your comment would be like, yeah, if there is a case like that, then that would be an error. But thanks for letting us know anyway. Okay, so 준우님 발표. 황현진님께서 또 질문해 주셨네요.
네, 네. 하은지님께서 물어보신 게 맞고요. 뭐 마지막 거 써도 상관은 없어요. 왜냐면은 어떻게 보면은 가장 최근에, 그러니까 저희가 이제 인타임 후에 3시간이 가장 그러니까 사망 시간 가장 가까운 그 차트 타임이잖아요. 그래서 그걸 쓰는 것도 나쁘진 않은데, 사실 뭐 보시다시피 이게 피처 하나하나에 다, 그러니까 아이템 한 개 한 개 집중을 하다 보면은 그 시간이 너무 오래 걸리고, 그리고 그거를 뭔가 엄청 깔끔하게 처리한다고 해서 성능이 오르지는 않거든요. 그래서 사실 마지막 걸 쓰든 맥스 민을 쓰든 이게 뭐 제가 뭐 많이 테스트를 해보고 고른 게 아니라 그냥 뭐 적당히 괜찮은, 경험적으로 좀 괜찮았던 걸 쓴 거라서. 근데 뭐 맥스를 그냥 그 마지막 차트 타임 거 가져오는 게 더 좋을 수도 있어요. 뭐 그리고 네. 그리고 뭐 아까 그 소로가 이제 정합성 관련된 질문을 하는데, 그 정합성도 마찬가지로 이게 워낙 애초에 이거 정합성 맞을 거 기대를 할 수가 없거든요. 그래서 하나하나 다
그쵸.
따지다 보면은 그 뭐 에이지도 300살도 있고 막 그래요. 최장수한 사람이 제가 알기로는 150살 이런데 뭐 300살인 사람들도 한 100명 있고, 그래서 그런 거 하나하나 다 처리를 했던 적도 있거든요. 근데 사실 그렇게 처리를 하면은 그 끝이 없어서, 정합성은 어느 정도 그게 좀 소수라고 판단이 되면은 그냥 저는 무시하고 진행했습니다.
네, 그리고 형진님도 말씀해 주셨네요. 조건에 맞는 거 한 160만 레코드 정도는 이제 판다스로 잘 되었다라고 이제 같이 해주셨네요. 네, 감사합니다. 그러면은 혹시 또 더 질문 없으시면은 일단 요 정도로 마무리를 할까요? 승우님 또 질문해 주셨네요.
맞다. 아래는 설명 안 드렸는데, 사실
네.
그 아래는 같은 경우는 지금 제가 한국보다 더 복잡해지거든요. 일단 이게 이레귤러한 그 타임 스텝으로 찍혀 있으니까 이거 선택을 해야 돼요. 그러니까 교수님이 처음 제안한 방법대로 그 차트 타임도 하나의 피처 디멘전 넣어가지고 표시를 할지, 아니면은 처음부터 그 틀을 만들어가지고 할지 이런 걸 결정을 해야 되는데, 저는 틀을 만들었었거든요. 그러니까 3시간이면은 이제 그걸 15분 간격으로 나눠가지고 이제 매트릭스를 만든 다음에 거기서 저희 갖고 있는 차트 타임 아이템들을 이제 하나하나 집어 넣는 거죠. 그렇게 하면은 어떤 거는 미싱 밸류가 생기고 어떤 거는 이제 다 채워질 수도 있잖아요.
그렇죠.
그래서 그거를 이제 썼는데 사실 효과가 좀 미미했어요. 그리고 더 뭐 의미가 좀 없겠더라고요. 그래서 성능 향상이 엄청 미비했었고, 그 시퀀스로 해서 써도. 네, 피처 엔지니어링. 네, 그리고 그 로지스틱 썼던 피처를 써서 했을 때 오른 거 보면은 뭐 피처 엔진 효과가 있긴 한 것 같은데요. 근데 시퀀스를 뭔가 잘 써서 성능을 올릴 수 있을 것 같지는 않았어요.
네네. 그게 사실 이제 우리가 3시간 정도의 정보만 가지고 24에서 48시간 내에 일어난 이벤트를 예측하는 거기 때문에 그 시퀀스가 그렇게 중요하지 않을 수도 있어요. 제가 수업 때도 말씀드렸는데, 그러니까 3시간 사이에 일어난 일들을 백오브 워드로 처리를 하거나 하든 시퀀스로 처리를 하든 24시간 후에 일을 예측하는 데는 크게 상관이 없을 수도 있다는 거죠. 우리가 예를 들어서 뭐 12시간치의 정보를 본다, 또 24시간치의 정보를 본다면 그 바로 다음 걸 예측한다. 이러면 이제 시퀀스가 굉장히 중요한데, 이제 그 일의 순서가 굉장히 중요한데, 그게 아니라 아주 조금의 그 초기의 정보를 가지고 먼 훗날의 미래를 예측하는 거는 사실 그 간격이 굉장히 뜨잖아요. 그러니까 3시간 이후부터 24시간 전까지 이제 21시간의 간격이 뜨기 때문에 뭐가 먼저 일어나고 뭐가 늦게 일어나는지 그렇게 중요하진 않을 수도 있어가지고, 말씀하신 대로 그 로지스틱 피처를 그대로 사용을 해도 아마 잘 될 겁니다. 네. 어쨌든 근데 말씀하신 듯이 피처를 그냥 막 쓰는 것보다는 이렇게 좀 케어를 이제 좀 정성을 쏟아가지고 하면 이제 확 오르긴 하죠. 그러니까 초반에 노력을 약간 그게 디미니싱 리턴이 있거든요, 얘도. 그래서 피처 엔지니어링 조금만 하면은 이제 확 오르는데, 그 어느 순간 이후부터는 이제 막 이 케이스 바이 케이스로 다 따져들고 막 도메인 널리지 퍼붓고 해도 잘 안 오르는 경우가 있어요. 그래가지고 뭐 대부분이 그렇고 사실은. 그래서 이 아무리 딥러닝의 시대라고 해도 이제 프랙티컬한 모델을 그러니까 이제 아카데믹 리서치가 아니라 프랙티컬한 모델을 만들 때는 이 피처 엔지니어링이 필수예요. 이게 그래야지 성능이 확 올라가거든요. 그러니까 조금만 신경 써가지고 뭐 노멀라이징 해준다던가 피처 스페이스를 줄여준다던가 이런 것들 좀 해주면은 이제 성능이 확 올라가기 때문에, 그런 거를 잘 알고 실제로 그런 건 이제 코딩 실력이 많이 중요하거든요. 엔지니어링 실력과. 준호님은 뭐 제가 알기로 회사에서 일하다 오셨기 때문에 아주 뭐 그런 부분은 문제가 없을 텐데, 여기 계시는 이제 회사 경험 없으시고 이제 계속 학교만 계셨던 분들은 좀 엔지니어링 이 프랙티스를 좀 자주자주 해주시는 게, 뭐 케이글 같은 거 하시든가 뭐 프로젝트 하시든가 회사 인턴 같은 게 굉장히 좋은 경험이거든요. 회사 인턴 하시든가 해가지고 좀 그런 걸 알아두시면은 나중에 일 처리 속도라든가 여러 가지 프랙티컬한 면에서 도움을 많이 받을 수 있습니다. 형진님이 네 커멘트 해주셨네요. 아르네 넣는 피처가 늘었는데도 성능이 떨어지는 건 오히려 탐색 공간이 늘어나서 짧은 앱공만 제로. 그렇게 보셔도 되고요. 근데 이게 에폭을 더 돌린다고 해서 더 올라가고 꼭 그런 게 보장되는 건 아닙니다. 왜냐면 지금 이제 피처가 RNN 같은 경우는 애초에 그 파라미터가 크잖아요. 모델의 파라미터가. 그래서 로지스틱보다 로스는 잘 떨어질 수도 있어요. 트레이닝 로스는. 근데 이 테스트 쪽에서의 성능이 안 올라가는 걸 가능성이 더 높습니다. 오버피팅이 일어나가지고. 그래서 이런 건 이제 데이터가 더 많거나 이럴 경우 이제 더 그런 면에서 좀 접근을 해야 될 것 같아요. 뭐 이폭을 많이 돌린다고 이제 항상 능사는 아니기 때문에. 네. 승우님, 보통 시퀀스 길이가 충분하다고 할 때 보통 타임 갭 어느 정도 등급, 그러니까 첫 3시간과 24시간 오버인데 그럼 좀 갭보다 갭이 중요합니다. 그러니까 3시간 안에 100만 개의 시퀀스가 있어도 24시간 후를 예측하는 데는 시퀀스가 그렇게 중요하지 않을 수도 있다는 거예요. 제가 아까 말씀드린 거는. 그래서 예를 들어서 뭐 오늘 하루 일어난 일을 시퀀스로 나열한 다음에 10년 후를 예측하라, 이런 게 무슨 의미가 있겠나 이거죠. 그러니까 그런 건 의미가 없고 그 갭이 중요한 거예요. 갭이. 근데 갭을 이제 제가 굳이 3시간을 둔 거는 이 뭐 예를 들어서 12시간치를 쓰라 그러면 이제 그 시퀀스 길이가 엄청 커지거든요. 그래서 그런 걸 처리하는데 또 다른 또 어떤 엑스트라 에포트가 필요해요. 처리를 하는 데 있어서. 그래서 그런 거를 이제 방지하고자 그냥 3시간만 써라. 3시간만 쓰면은 차트 이벤트 그냥 쭉 나열해도 대략 뭐 100에서 200개 사이로 이제 마무리가 되기 때문에. 근데 실제로는 이제 더 내가 예측하고자 하는 시점에 가까울수록 그 가까운 피처를 쓸수록 당연히 예측 정확도가 올라가겠죠. 근데 그렇다고 막 뭐 24시간 후에 죽을지 말지 예측하는데 뭐 23시간까지 피처를 쓰면은 1시간 후에 미래밖에 예측을 못하는 거잖아요. 근데 이제 제가 예전에도 몇 번 말씀드렸는데, 예를 들어서 하트 페일리어라고 치면은 이거는 이 사람이 실제로 심장이 고장나기 1년 전엔 예측을 해줘야 돼요. 예를 들어서 하루 전에 예측을 하면 아무 의미가 없어요. 왜냐면 이미 심장 고장날 대로 고장났기 때문에 고칠 수가 없거든요. 그래서 그런 어떤 이제 이 페이털한 디시즈 같은 거는 이제 최대한 빨리 예측을 해줘야 되는데, 그 최대한 빨리가 언제냐? 그건 이제 다 도메인 널리지가 좀 필요합니다. 그러니까 이제 뭐 예를 들어서 하트페일리어 같은 경우는 최소한 6개월에서 1년 정도 예측해줘야지 이제 의사가 뭐라도 해볼 수가 있다. 뭐 이런 거는 의사가 아니면 사실 모르잖아요. 그래서 그런 문제 정리를 할 때에는 도메인 엑스퍼트와 같이 이제 논의를 하셔가지고 문제 정리를 해야 됩니다. 그래서 이제 어떤 리즈너블한 타임 갭을 두고 그 전까지는 최대한 많은 피처를 사용을 하는 게 제일 성능이 좋겠죠. 네. 네, 좋습니다. 그러면은 요 정도로 마무리하겠습니다.
네,
네, 수업
감사합니다.
마무리는 아니고, 네, 준우님의 발표 마무리. 네, 감사합니다, 준우님.
네.
All right. So before we begin with the rest of the material, I would like to say that I would like to emphasize something that Juno actually shared during his talk, which was that he does, even though he has almost zero domain knowledge regarding healthcare, I would say not zero because he actually dealt with EHR data quite a lot, but still, he's not a doctor, and so am I. I am not a doctor, so nobody's doctor, right? In this class, so nobody actually went to medical school and has a medical license. So assuming that nobody is a healthcare expert in this class, then nobody has domain knowledge, but still they were able to, some of the students, I mean, most of the students were, they achieved the AUPRC score of, like 10% or 20%, which is decent enough. But for some students, some exceptional cases, such as like Junwoo himself, was managed to achieve almost 0.5 AUPRC, 0.4, I think it was like 45% or 50% AUPRC, even without any domain knowledge, without actually using any domain knowledge. What he did was purely statistical. It was just using the top K most frequent features, and then filling in the gaps and actually doing blowing up the one-dimensional numeric features to three-dimensional vectors, and all those like numeric, all those like engineering efforts and statistical approaches. Those were enough to build a very accurate model. So that actually tells us a lesson. Like, do we really need domain knowledge at all? But as I said in Korean, if you're academically or theoretically, if you have infinite amount of data and infinite capacity model, you probably don't need domain knowledge. But in reality, when you're employed by a company like like IT company like Naver or Google or whatever, if you got hired by a company to build a predictive model that can actually sell to clients, then you need to build a very accurate model. And most in reality, you don't have infinite amount of data. You don't have infinite capacity model. You don't have infinite amount of time. So you have to optimize. And when you're optimizing, domain knowledge is crucial. So theoretically, academically, domain knowledge is not necessary, but in reality, it still is very relevant. So that is why you should, and also feature engineering also as well. So feature engineering and pre-processing your data well, and you're putting some effort into that pre-processing, and actually coming up with some even simple feature engineering schemes like what Junwoo did with statistical approaches and chi-squared feature selection. Those really help a lot. So please don't disregard them. If like when people study AI as an AI research student or AI researcher, people tend to ignore the importance of feature engineering. But actually, it is still very relevant. So hopefully you can, as I said in Korean, you can maybe experience that kind of feature engineering and basically engineering practice by going to an internship at large IT companies or small IT companies as well. I think that's irrelevant. Like the size of the IT company is irrelevant because wherever you go, you are going to deal with a lot of raw data, which requires a lot of pre-processing data, feature engineering. So hopefully you can get some experience like that. All right, so if there are no more questions, then I will proceed with the class material. So far, last time we talked about the exploiting or taking advantage of the domain knowledge, which is in the form of directed acyclic graph. Typically, in our case, it was actually a tree. So we utilized a ICD-9, actually not ICD-9, so a diagnosis code hierarchy or diagnosis code taxonomy. So there was like the highest place there was a root, and then in the lowest there was a most granular concept, granularly defined or fine-grained defined this diagnosis concept in the bottom as a leaf node, and then we assume that a single fine-grained disease concept could be represented as a chain of its lineage, and that's how we show that leveraging that kind of domain knowledge actually made the model more robust to small data regime, like when your training data has low volume. And we also looked at the data, the visualizations and the attention behavior. So today we are still going to deal with the graph, but this time we are not going to rely on external graph. So when I say external graph, that means we actually used diagnosis code hierarchy, which is not in the EHR itself. So EHR is a data that is dumped inside the hospital database, relational database typically, and taxonomies like SNOMED CT, drug network, CPT code hierarchy, those are not within the hospital data warehouse. Those are outside. So that's why I call them external graphs. But this time we're going to actually interpret EHR as a graph. So EHR itself can be a graph, and they actually encode a lot of domain knowledge. And so we're going to look at how we can use them and how we can actually learn them. We don't have a lot of time, so hopefully I can finish that in maybe 40 minutes. So as I said, EHR data are stored, can be seen as a graph, but first of all, back to the basics. So EHR data are stored in a relational database. So here, this is a comprehensive database information, the information stored in database for a single patient. Because usually the patient table is at the top of the schema. If you remember the mimicry schema, there was the patient table at the top, and then in the right beneath the patient table there is the admissions table, and beneath the admissions table there was the ICU stays table, and so on and so forth. So here we're going to assume that this is the outpatient setting. So there is the patient ID at the top, and then the patient makes a sequence of visits over time, over like few years, over the entire lifetime or whatever. So each visit or encounter has a unique identifier. So of course, patient has an identifier like 주민번호, and then encounter ID or visit ID has an ID. So those are all stored in the admissions table or encounter table as an independent or as a separate row. And then within a single visit or encounter, there are a lot of information that occurs within the hospital. For example, as I said, this is a outpatient record, 외래 환자입니다. 그러니까 이제 입원이 없고 바로 들어갔다 나오는 거예요. 그래서 in that outpatient setting, the first phase that the patient goes through is usually diagnosis. So the doctor talks to the patient and then try to figure out what's wrong with the patient. So that would be the diagnosis. So assume that there are 5 diagnosis codes. So this patient received within the visit 5 diagnosis codes: fatigue, cough, fever, abdominal pain, and chest pain. And because of the cough and fever, the physician decided to give him or her, the patient, medicine, acetaminophen, which is Tylenol. So, and then there would be the start date and the end date. So when to start taking the medicine and when to stop taking the medicine. And the instruction is like, take it 3 times a day after the meal orally, something like that. And that was, so due to that would be ordering or prescribing this medicine for this and this cough and fever diagnosis. So there's a reason for prescribing this medicine. And then for this guy, for benzonatate, which is another type of medicine, this is prescribed due to cough only, and it has its own set of information. For fever, sometimes if you're like high in fever, or if you're like really tired or something, 병원 가서 수행 맞으시잖아요. So something like IV fluid. So because of the fever, a doctor prescribed a procedure. This is not a medicine. This is a procedure. So the procedure, some procedure order. So individual orders also have unique identifiers. Like this is a medication order, this is another medication order, but the medication order themselves are given unique identifiers, obviously. So are procedure orders, and this procedure order is tied to the information or specific procedure code, which is IV fluid. And due to abdominal pain and chest pain, the doctor prescribes a procedure or orders a procedure that is actually a cardiac EKG. 그러니까 심전도 검사 한번 해봐라. 그래서 and the cardiac EKG comes with, if after the cardiac EKG would come with a set of numeric values. And there are some other like family history, some basic vitals like blood pressure, heart rate, weight, height, tobacco use, or some hereditary things like something like that. But those are like so. But the core information would be the diagnosis, the medication, and the procedure, and they form a hierarchy. They form a hierarchical information. So at the top is patient, right beneath is encounter, right underneath that would be diagnosis, and the diagnosis would lead to ordering certain medications or procedures. So there's a set of it's like a pretty similar to diagnosis hierarchy actually, but this is more heterogeneous entity, graph of heterogeneous entities. And so this would be a graphical representation of the EHR. And this is actually easier for the humans to understand what's going on instead of actually looking at a bunch of tables and then joining them because of all the foreign keys and primary keys and that kind of stuff. So actually we can simplify this into this. So we will only take the core information. So there is a sequence of visits, and then the visit lead to diagnosis, and diagnosis leads to medications and procedure orders, and then some procedures would lead to actually some lab results or procedure results. So this is a 4-level hierarchy actually. And then, so this would be a simplified graph, and this information, this especially, so the black arrows are actually just given because like these diagnosis codes are just something you receive when you go to the hospital. But some EHR dataset actually it contains or stores this reason information, like when the doctor makes a prescription order or procedure order, the doctor has to write why he or she thinks this prescription is necessary or why this procedure is necessary. So this red arrow indicates that reason. So I'm ordering this because of this and this. I'm ordering this because of this and this. So there is there would be like a suspicion or reason. And this encodes this red arrow encodes or reflects physician's decision process. So they are actually domain knowledge. So if you just carefully look at the EHR data that stores this type of reason information, then you can easily learn how to recommend drugs for certain types of diagnosis or certain types of patients, actually, patients who have certain type of diagnosis. So we would like the model to learn this. If this information is available, this red arrow is available in your EHR, then we would like the model to actually encode this so as to better learn, the clinical practice. So that would be a bit like a regularization, another form of regularization. So before, what we did in the EHR with the logistic regression, or actually in the RNN. Outpatient setting RNN model architecture as well. What we did is we thought a single visit consisted of multiple codes, variable number of medical codes that could be diagnosis codes, medication codes, procedure codes, and any codes, and so certain set of medical events, so to speak. And then we would simply sum them up to represent a visit. So a sum of the embeddings of the codes was equivalent to the visit embedding, or at least we assumed that would be equivalent. So that is actually not the best idea that is not a best idea, because if these kind of information is available, then it is probably not the best idea to just simply add all the diagnosis, all the procedures, all the medication, all the lab results, embedding vectors together to represent this, because there is clearly a hierarchical information here. So that if you do this, then all burden falls on the RNN, which is the predictive layer on top of the visit. So if you're dealing with outpatient setting, then there will be a sequence of visits. So you would like to encode or embed a sequence of visits using or you would like to aggregate sequence of visits to derive a fixed size vector to represent the patient itself. So there should be an aggregator function, and in this case, we're going to assume that that would be RNN. So it could be 1D CNA, it could be transformer. Doesn't really matter, but just suffice to say that there is a prediction layer that aggregates the visits. So if you simply assume that a visit consists of flattened structure, then you're putting all the burden of figuring out the relationship between these codes to the aggregator layer on top of the visit, which is not a good idea. I mean, eventually if you have infinite amount of data and like infinite capacity model, then the model would actually figure out the information, the relationship between them. But if normally that is not the case, so if this kind of information is available, it is probably a good idea to encode them. So the first to do this this kind of work, or to interpret EHR as a graphical structure, was mine, which is actually my paper, but that it's not really important. The concept is important. Trying to figure out, trying to view EHR as a knowledge graph or graphical structure, that is the important concept here. So in that paper, this is just an idea. So you don't have to actually memorize all this, because there are a million different ways to deal with graphs. The important thing is to view EHR as graphs. But in this specific paper, what I did is to aggregate, so to add another layer. So underneath a visit, there is a diagnosis level, and then underneath the diagnosis level, there's the treatment level. And the treatment actually is the sum of all the medications and the procedures. So so the visit is no longer sum of all codes, but the visit is sum of diagnosis objects. So there is diagnosis object 1, 2, 3, 4, 5. So each diagnosis object contains a single diagnosis and the attached treatments. So since this guy, fatigue, doesn't have any treatments attached to it, then it itself becomes a diagnosis object. And then diagnosis object 2 is cough and its related or attached treatments. And the way you encode or derive diagnosis object 2 is actually, you can have there's also millions of varieties, but what I did is actually to use a bilinear matrix for like an approximation of bilinear matrix operation. But again, that's just like a detail. So the important thing is the visit itself is now a sum of diagnosis objects. So there are 5 diagnosis objects. So you derive diagnosis object embedding individually, and then you aggregate them to derive the visit embedding, and then you aggregate the visit embedding to derive the final patient embedding. So that would be like a hierarchical approach or bottom-up approach. So compared to that, so previously there was no such approach like that. So all the baselines are actually just flattening approach. So a visit is represented as a flattened structure, like a individual unrelated code, like a bag of codes, just like bag of words. I would like to call them bag of codes. So these all these 4 are bag of codes, or actually 5. These 5 baselines are all bag of codes approach that doesn't care about the hierarchical structure. But fortunately, Sutter Health dataset, they actually do contain the reason information, the red arrows. You can actually lay out the hierarchical structure of the EHR. So you can actually use this graphical approach. So compared to all the baselines, all the bag of codes baseline, which is 1, 2, 3, 4, 5, 6. Compared to that, these two variants of the graphical approach perform better, especially when the number of training samples are small. So you can think of why it is quite obvious why this is so, because in coding, physicians' decision process is just like regularizing. So you are actually decreasing the size of the hypothesis, hypothesis space. So you're guiding the model to only look at hypothesis where this kind of information is valid, so we are not going to consider the case where fatigue is actually concerned with acetaminophen. That is not in our hypothesis space, because we're actually respecting this hierarchical information. So that is why I said that the hypothesis space is now decreased, but it is decreased in a meaningful manner, because our narrower hypothesis space is actually very closely tied to physician's decision process. So it is a valid hypothesis space. So in a smaller hypothesis space, we need lesser number of data to learn an optimal classifier. So that is why mine is actually showing better performance in lower data regime. Hopefully that is. Oh, by the way, I didn't actually describe the task. The task is actually to predict a heart failure onset with a one year time window. So given 18 months history, we've seen that in the retain as well. Right, so that is the important lesson here. So when the data set increases, probably when the data set is infinite, then the graphical approach and the bag of approach doesn't really, there should be no difference between the two. But as I said, that is not always the case. Like the infinite data is never available. So this is one way to look at it. Another way is to actually see when it helps, when the graphical approach actually helps. So we actually need to consider the complexity of the visit. So when I say complexity of the visit, I mean how many diagnosis codes there are within a single visit, and how many treatments were prescribed, and how many procedures were prescribed. Because if your visit only contains a single diagnosis code, then this kind of graphical approach really isn't necessary, because there's only one node in your visit. So there's no graphical structure to consider at all. So this is trying to see when this graphical approach helps. And so these 6 are the same baseline, bag of code baseline. And when the visit complexity increases, so visit complexity, you can just think of visit complexity as a measure of like whether there are how many diagnosis codes and how many treatments there are connected to each diagnosis code. So these are the most complex ones, and these are the most simplest ones. And you can see that the easy ones, the visit complexity with the least complex visit groups, the performance is actually not that the performance gap between the graphical approach and the non-graphical approach are not that wide. So you can see that the Med2Vec is actually the best performer here. And still, like MIME and MIME variant, compared to their performance, tanh, or simply just aggregating all the codes and then putting that through a nonlinear activation function tanh, or actually linear activation function, performs just as well as MIME and MIME variant. But when you go to the really complex visits, like like at least 3 or 4 diagnosis codes with a lot of treatments attached to it, that is when the graphical approach actually shines. So you can see that the performance gap between MIME and all the other bag of codes approach variants are just, it is wider now. So that is another way to look at it. So you can assume that this kind of graphical approach is only valid when the visit structure is complex enough, which is actually pretty obvious. This is actually another task. So with the same Sutter Health data set, we can do the heart failure prediction, but we can do what I said as a language model for EHR, which is to predict the next visit's diagnosis codes. And now you can do the same thing as GRAM, where you have different buckets for different, depending on the rarity of your diagnosis codes. So these are all rare codes, and these are really prevalent codes. And you can see that some really rare codes doesn't really work well for all the baselines, but I'm not sure why, but Med2Vec is actually outperforming all the other. But for relatively rare ones, like in the 40th to 60th percentile, or 60th to 80th percentile, using graphical structure actually helps a lot, because as I said, they're encoding physician's decision process. So that is actually encoding domain knowledge, or equivalent to injecting domain knowledge. It would be another way, because previously we looked at GRAM, where we were injecting domain knowledge from the external source, but now we're injecting knowledge from the internal EHR dataset. So that is another way to look at it. All right, so the conclusion is that EHR structure, if your EHR structure contains the reason code or the red arrows, then it is actually encoding very rich physician's domain knowledge, or physician's decision process, and explicitly architecting your model to respect the kind of information would lead to better performance when your data set is, relatively small. So that would be the lesson here, that the graphical structure of EHR is actually very important. So, and that is not what we did so far with the project number 1. Project number 1, we just didn't care about all the graphical structure. We just, aggregated the events in a flattened manner, and then we just appended them. We just concatenated them, and then we just pour them into the RNN. So that's what that still works quite well. But if you want those extra performance, or if you want your model to be robust to a small data set, then you might want to consider the graphical structure. So that was MIME, or actually, if you think about it, MIME is actually a very special case of graph neural networks. So you can easily use graph neural networks instead of MIME, which is a bit more intricate. You don't have to do that. You can just simply use graph neural networks to encode this kind of graphical information. So you can just simply represent these 1, 2, 3. How many codes? How many codes there are? 1, 3, 5, 9, 12. So there are 12 codes, 12 events. I would say events. So 12 events, and you can view them as 12 node graph and represent them as with the adjacency matrix, and then you can push them through graph neural networks to derive a visit representation, this. So that would be the easier version of MIME, and that would also equally work well. But the problem with all those graphical approaches is that those approaches are only applicable when your EHR dataset does contain this reason code, these red arrows. So the problem is the red arrows are not always available. So fortunately, when I was doing this kind of research, Sutter Health dataset did contain those reason codes. So it was it was straightforward to represent your EHR as a hierarchical graph, but not all EHR contains that kind of information. For example, like Mimic3 does not contain reason code. If you remember the Medicaid prescription table or the procedure table, they don't have a field called reason or something like that. So there is no red arrow information in the Mimic3. Also, not for EICU as well. So, and if you think about Shinpyeong dataset, they certainly don't have that kind of information. So usually claims data don't have that kind of information. So it is safe to assume that your EHR data would not contain those reason codes. I've only seen maybe handful of EHR data set when I was dealing with the Sutter data set, or doing some projects during my PhD, or doing some projects in the Google Health. I've only seen like maybe like 5 or less than 5 EHR data set that records this reason information. So that is one. And another thing is these association edges, the red arrows, are not really accurate. Statistically, asymptotically, they would actually converge to accurate information. But sometimes the reason so the hospital might force the physicians to put or store these reason information when prescribing a medicine. That is one way to store reason information in your EHR. Like when you're a doctor, when you're a physician, and you're trying to order a medication after talking to a patient, you need to click those information. Like what kind of medication you want. So there would be like a drop down menu, and then you select a medication, and you select the amount, like 10 milligrams, 20 milligrams. Like when you select all those information and then you try to hit the prescribe or the order button, it would not let you go unless you fill in the reason field, like why you're trying to order this medication. So that is one way to store reason information. But some physicians might actually be annoyed by the process, like every single time trying to write the reason code why I'm trying to order this medication is very, it would not be a fun experience. So some physicians might actually just put random things into it and then just click the order button, because at least he or she knows what they're doing. They're actual medically licensed experts. So that is why the association edges are actually quite noisy. Right, so because of those two information, graphical approaches might not be the best idea. And especially, I would say the first one is actually the most important one. So in that case, what are our options? So if structure information being the red edges, if structure information is available, we can design a special model to reflect the structure, the physician's decision process, such as mine, or we can simply use graph neural networks. If the structure is not available, what are we going to do? So that is the question. And obviously, we can do what we used to do, which is bag of codes approach or bag of features approach, or we can think of using a graph neural network where the adjacency matrix is all one. So we're going to assume that everything is connected to everything else. But if you think about it, these two are equivalent. So if everything is connected to everything else, then it is just as good as bag of features. Hopefully that is clear to everybody. So yeah, so if the structured information is not available, are we going to revert back to the old ways? And I would say that is not the best idea. So another way to actually deal with when the structured information is not available, one way is to actually start from a fully connected graph and then sparsify. So we assume that, so this is a visit. There's a visit node at the top, and then let's assume that this visit consists of 5 medical events, 2 diagnosis codes, cough and fever, and 2 medication codes, that's it, aminophene and benzoate, and 1 procedure code, IV fluid. So 5 codes, and we're going to assume that everything is connected to everything else. So it's a fully connected graph. And then as we learn, as the model learns, we are hoping that the model would focus on more important relationship or important edges, and then just disregard or just remove or weaken the strength of irrelevant or unuseful edges. And this is certainly possible when you use a attention network. So those who actually attended or audited my class in the previous semester, the programming for AI, you would understand, or hopefully you would remember the connection between the transformer, self-attention, and the graph neural networks. So, but for those who are not, I'm just going to briefly describe them, why the two are actually similar, belong to this equivalent, class of equivalent family of functions. So if you remember the transformers, we're going to only assume we're going to deal with the encoder. So if you think about the transformer encoder's self-attention, if you think about that, it is attending. So individual words so let's say assume that this is the given sentence. So I like going to movies, 6 words or 6 tokens. We're going to deal with this we're going to handle this example. And if you think about the self-attention process, every single token attends to all the other tokens, including itself. Actually, there should be a self loop here. So as I said, every single token is attending to all the other tokens, including itself, and every single token is taking its turn. So I is attending to itself, like going to movies, in its own way, and like, which is the second token, is also again attending to I, itself, and all the other tokens in its own way. So every single thing is attending to every single other things, which means that transformer self-attention is implicitly assuming the tokens are fully connected. So it's a fully connected graph, which the strength of each edges are not predetermined. It is determined by the attention process. It is determined by the model. So there is the connection. So if you think about self-attention formulation, so this is the dot product, scale dot product, or QKV operation. So this part, softmax QK transpose divided by the square root of the dimension size, that amounts to a normalized attention map. And this is multiplied to the value embeddings, the value, just the value embeddings. So there will be individual value embeddings for each token. So I like going to movies, the N symbol, and so doing a matrix multiplication between these two would be this row, doing the dot product with this column. This is not a column. This is actually a matrix, but I'm just going to assume that this is a column. Like each word embedding, each value embedding is just a token. So this is a dot product between the two. That would give you this first row, and dot product between the second attention, which is the attention given by the like token to all the other tokens, multiplied by this this column would give you this row here. And you do this so on and so forth. So that is the QKV operation. And you can see that this is simply, if you think about this row, this is simply a weighted sum of this attention weight with this value embeddings. And the second row is, again, a weighted sum between this set of attentions with this value embedding, and so on and so forth. Graph neural networks, or graph convolutional networks, actually. So this is a specific form of graph neural networks, graph convolutional neural networks, where there is a adjacency matrix of A prime, which is adjacency matrix filled with the diagonal elements filled with 1. So we're adding the self loop to all the nodes, and then we multiply the D inverse, which is the degree matrix. So this is if you think about this D inverse A prime, this is a normalized adjacency matrix including a self loop. So I just wrote down just random adjacency matrix, but it is a normalized. So sum of this row would be 1, sum of this row would be 1, which is similar to attention metrics here, sum to 1 and sum to 1. And XW, so this is actually a single graph convolution. So if you stack this multiple times, then you're actually doing like 2 hops, 3 hops, and 4 hops, but this is just a single hop. And the F is, you can think of F as just nonlinear activation function. And so we're just going to forget about the nonlinear activation function. So just focus on D inverse A prime XW. D inverse A prime is the normalized adjacency matrix. XW is the node embedding. And if you do the matrix multiplication of the two, then this is simply a weighted sum of the adjacency matrix and the node embeddings. And another adjacency matrix, another adjacency vector, weighted sum with this node embedding, giving you this row. So those two are very, very similar. So mathematically, graph neural networks can be seen as a chain of MLP with graph convolution. Transformer can be seen as a chain of self-attention followed by MLP, followed by position-wise feed-forward network. So those two are very similar. So there is a one-to-one map between one-to-one correspondence between the two. So D inverse A prime would be the same as self-attention, but this adjacency matrix is fixed. It is fixed by the data, but this attention map is not fixed. It is determined by the attention process. But these two serve the same purpose. And then the node embedding is the same as V here, which is this guy. So so the node embedding and the token embedding are the same thing. So that is why I'm saying that transformer itself is actually a generalized graph networks, generalized graph convolution neural networks. So transformer is like a superset of graph neural networks. So we can assume that, going back to the motivation, how are we going to do this is to actually use transformer. So we're going to use transformer self-attention process which assumes that everything is implicitly fully connected, and then we're hoping that the model would learn meaningful attention strengths to reflect the physician's decision process or latent information, because these red arrows are not given to us. It is latent information. All right. Oh, sorry. So yes. So this is the motivation behind graph convolution transformer. Another, like a hybrid. This is a model that is the hybrid of graph convolution neural network and transformer. So the motivation is to guide the transformer to learn meaningful graphical structure. So if our visit structure looks like this, then hopefully, starting from random attention map, hopefully transformer would recover this adjacency matrix that is representing this visit structure. And obviously, if there is infinite amount of data, this actually works. I've seen this work with like 7 million patient records. This actually worked with just vanilla transformer, which is pretty impressive. But we don't always have 7 million patient records, so we need to actually regularize the transformer to better learn this information, this adjacency matrix / attention map. So one way to do it is to actually use a conditional probability between a pair of codes that you can calculate from the data from your training set. So what I did is to actually look at all the visits. So I would go through all the visit records, and within a visit there are multiple medical codes, medical events, and you would calculate a conditional probability between a pair of codes that occur within the same visit. For example, what is the probability of EKG occurring when there is chest pain in the visit? So, this is just a conditional probability. So you just need to calculate the empirical occurrence probability of individual codes. Like, what's the probability of chest pain occurring in a visit? What's the probability of fever occurring in your visit? What is the probability of fatigue occurring in your visit? And then you just simply calculate the conditional, and then you also calculate the joint probability of the pair of codes, pair of medical events, and then you can calculate the conditional probability. So you do this with your training set, and then using that conditional probability, you input, you initialize your prior attention map. So this is a conditional probability matrix P. For example, if your visit looks like this, there are 1, 2, 3, 4, 5, 6, 7, 8 codes. If there are 8 codes in your visit, then you find a correct correct coordinate, which is here. You can see that if you've calculated this, like what is the probability of EKG given chest pain, that would be here. So chest pain and EKG. So you put this conditional probability value here as a prior. And then for this, if you calculate what is the probability of QRS occurring when benzonatate is in the visit, then you could encode or fill this block here, which is benzonatate and QRS, fill this block with this conditional probability. So you do this for all blocks, and of course, some blocks should be fixed to some value, like the self loops and the visit itself, because visit is always connected to the diagnosis codes. So some blocks are predetermined, and some blocks are blocked actually, because you don't want benzonatate to attend to cardiac EKG. You don't want fever to attend to QRS duration, because you know at least some certain loose structure of the visit. So some blocks are some cells are blocked, some cells are predetermined, and some cells are filled with conditional probability. So that would be your prior information injected attention map or adjacency matrix. So this is our beginning. This will be the basis of our regularization. And then, so regularizing the attention would look like this. So you start with the n by n conditional probability matrix P, which is this. So you fill this, you initialize this. Which you can certainly do by going through all the data. And then you have the matrix P, which is actually pseudo adjacency matrix. You can see this as a pseudo adjacency matrix. And then after this, so you start with a graph convolutional neural network with this P, which is determined. And then after that, you start stacking self-attention layers, the transformer blocks actually. You start stacking transformer blocks, which is AJ, and then you regularize the attention of these the subsequent attention blocks with KL divergence between P and AJ. So the first block, the first block right after the matrix, right after the graph convolutional neural network. So that would have a regularization value like this. So you start with P, which is predetermined, and you don't want your AJ, you don't want your first attention map to diverge too much from your pseudo adjacency matrix. You want them to be as similar as possible. So that would be for your first attention block, and then the subsequent blocks would actually follow the same reasoning. You don't want your third attention map to diverge too much from the second attention map, and you don't want your fourth attention map to diverge too much from the third attention map, and so on and so forth. So it's a chain of KL divergence terms. And then that would be a regularization term. So that is still a supervised map. It is still a supervised classifier. You're still trying to classify heart failure prediction. You're still trying to predict mortality, whatever. You're trying to predict something. So it's a supervised model, but it is regularized with this attention map regularization with KL divergence. So in sentence, you are starting with prior knowledge P, and then you're slowly evolving the attention map to maximize the supervised learning per task performance. That would be the one sentence summarization of the model. So you can do this. So I've tested this with two different data sets, which is one is synthetic and another is EICU. So I use synthetic because I didn't the data set was not a data set with the reason code. So in order to evaluate whether this graph convolution transformer GCT is learning a meaningful structure, we need to actually know the ground truth structure. Like we need these red edges here. Like we need to know the ground truth structure to evaluate whether the model actually learned the structure. So, but at the time I didn't have the EHR data set with the ground structure known, so I had to actually come up with a synthetic one. I had to simulate a data set. So I actually synthesized a 50,000 patient visit records, and when I was synthesizing, I was using Pareto distributions, because if you when you study the EHR, it is a very long tail distribution. Like only few diagnosis codes are used all the time, and only few medication codes are prescribed all the time. So you can calibrate your Pareto distribution carefully, and then using that you can sample the hierarchical structure of your EHR. So I did that, and then for real world data set, I use EICU, which is which is a bit larger, not bit, but which is way larger than Mimic3. So synthetic data to evaluate whether GCT learns correct structure, Philips EICU too. So note that EICU doesn't actually have a structure information available. So using the synthetic data, it is the synthetic data is used to evaluate whether the model reconstructs or recovers the structure information well. So we're doing a graph reconstruction task. So given a pair of those, we're trying to predict whether there should be an edge between the two or not. So that would be the task. And you can see obviously with the ground truth adjacency node, the model can easily recover. It can easily achieve perfect score, like because we already have injected the true adjacency matrix into the model. But for these, for the baselines, you can see that the GCT is outperforming all the other models. And so GCN random is just trying to inject random prior knowledge. Shallow and deep are not graph neural networks. They're just bag of codes approach. Transformer is just transformer without any prior knowledge. GCNP is graph neural networks with the the pseudo adjacency matrix used all the time. And GCT is the hybrid between GCNP and transformer. And you can see that the transformer is actually showing the best performance as far as the recovering the graph structure goes. And this is using GCN, using the GCT, comparing that with the baselines to do actual meaningful prediction tasks with the real world data sets. So we've done readmission prediction and mortality prediction, and compared to the baselines, GCT actually outperforms all the other, but only for readmission prediction. As far as mortality prediction goes, the gap between the GCT and the baseline is not that large. But here you can see some difference between the two. So these are the quantitative evaluation, but the interesting thing is actually the qualitative evaluation. So here, what we're trying to see is what the true connection and the learned connection between GCT and the true connection. So this is a single visit sample from the synthetic data set, and the bars are actually the true edges in the perspective of this guy. So this is so it's a single visit, and a single visit contains a lot of codes here, like a lot of codes. And then in the perspective of D199, this diagnosis code, it is connected to visit, obviously, and it is connected to 1, 2, 3, 4 treatment codes here. So that is the ground truth. And if you use simple transformer, to learn this kind of graphical structure, and I'm using 3 stacks of transformers. So this is stack 1, stack 2, stack 3. And you can see that in stack 1, transformer doesn't have any idea which code to attend to. So it is a more or less uniform distance. So the blue bars are the attention distribution, and it is more or less uniform. If you go to block 2, now it is learning something meaningful. So now it is attending only to these 2 codes, which is correct, but it is missing all the other codes. And then if you go to block 3, now it is attending to all the other codes. So it knows in somewhere in the process of attention, like chain of attention map, self-attention, it kind of knows which codes are relevant and which codes are not, but it is not always sticking to the ground truth relations. But if you use GCT, which is a hybrid between prior knowledge and the transformer self-attention, you can see that it is converging towards ground truth, the edges. So you start with this structure, so here, this is self-attention block 1 is not actually self-attention. This is pseudo adjacency matrix P. So there's a pseudo adjacency matrix P, and then you evolve from here to self-attention number 1 and self-attention number 2, and it is putting more attention to the ground truth edges or connections as it goes. So you can see that it is learning the ground truth structure pretty well. Right, so the GCT conclusion is that when the structure is not, the structure is not even available, the red arrows or the reason code not available, you can still do better than just bag of codes approach. You can actually try to learn the graphical structure as you go with the help of some prior knowledge. So that is the conclusion. And it actually gives you better performance, but not for all cases. Not like, you know, for readmission, it gave you better performance, but for mortality prediction, more or less the same. So yeah, that depends on which test you're trying to do. So that is the lesson. And this graphical structure, this graphical approach to handling EHR it's been around only for a couple of years, and I'm seeing a lot of papers that try to leverage, use this kind of notion or approach combined with external graph knowledge. So it is like combining EHR graph with like diagnosis code hierarchy, or EHR graph with drug network knowledge graph, or SNOMED CT. I'm seeing a lot of papers like this these days, even like, you know, like 2020 and 2021. So maybe this could have actually be the de facto standard way to deal with EHR data, but it has shortcomings, because EHR graph, if you think about the EHR graph, it is a really large graph. If you remember the size of the chart events table, which is 300 million rows, how to lay them out in a single graph would be, that would take like a gigantic amount of space. So there is some limitation and some challenges, like engineering challenges, and obviously not just engineering challenges, but also machine AI challenges as well. For example, how to deal with multimodal data, multimodal information, like codes and continuous values, like numerical values and text and images as well. How to deal with those kind of heterogeneous entity graphs better, and how to scale that to like millions of rows or like trillions of rows. Now, those kind of questions are still unanswered. Right, so yeah, this concludes the domain knowledge and graph section of our course. Are there any questions? Yeah, we have about, I guess this is, yeah, we have about 4 minutes, but if there are no more questions, I guess we can end the class today. Starting from next week, we'll go with the medical text, and the second project will be released. But if you're interested in doing your own projects, given that you've achieved a decent amount of score in project 1, you can actually try to come up with your own project and then consult me if that is actually some project that is worth doing. And if not, you can just follow the project number 2, which is the given project number 2, which would be basically handling clinical text in mimicry and then trying to build a simple classifier. All right, so that's the end of the class today, and have a good weekend, and I'll see you guys next Tuesday. Bye-bye.